Topic 2, Day 3, Composite Functions. So when we talk about composite functions, we have to be first aware of the domain and range of those composite functions. So as a quick reminder, domain represents all of the possible x values that work for a function, and we have two main notations to indicate the domain, the inequality and interval notation. If you look, I have a little graph drawn on the right-hand side, and when we're looking at the domain, we can see that the leftmost, or the most negative point, is at -7. And it's an open dot, which means it does not include the point -7, but anything really, really close to -7. And then not including, so we have the inequality, or you can use parentheses. Domain is our x values. And then our rightmost point is at 5, and that one is a closed circle. So it includes that point, and we can put a 5 there. So that's in inequality notation. And then interval notation will be parentheses, -7, comma 5, bracket, to indicate the including and not including. Range is similar, but for our possible y values. And again, we can use inequality and interval notation. Look at the same graph. Our lowest value is at -2. And you'll see that it passes by, right? It's a part of the function. It crosses through the point -2. So it's going to include, range is y values. And then our highest value is at 4. But again, that's an open circle. It does not include. So we use just a regular inequality without the equal sign. And then here, if we're using our interval notation, we'll use brackets first, -2, comma 4, parentheses. Now, when we talk about composing functions, you can think about putting a function into another function. So if you imagine these as our function boxes, right? We have some x that we're inputting into function g, and then whatever we get out, we would call g of x, right? Whatever the value becomes once you put it through the function g. And then you're going to put that output as the input into our next function, function f. And it gives us f of g of x, right? And this is saying that the input for function f was another function, g of x. What's important is we have this dot notation right here. And what you should know is this f of g of x is equivalent to saying f parentheses g of x, right? So the inside function, the g of x, is going into our f of x function. So let's take a look at this first teacher example. We're given two functions. F of x is x squared plus 2, and g of x is x minus 3, where x is the set of all real numbers. Find f of 3. So first, it's saying that if our x value is 3, what is our f of 3, f of x value? So we're going to plug in 3 for our x. 3 squared is 9, 9 plus 2. F of 3 is equal to 11. Okay, now it's asking for g of f of 3, right? And I'm just going to rewrite this as g of f of 3. And what's cool is we already know what f of 3 is. F of 3 is 11. So all we're having to do is actually put in g of 11. And here we do x is going to be 11 minus 3. G of 11 equals 8, which means g of f of 3 also equals 8. All right, try a student example on your own. Now for our second teacher example, we have two functions. F of x is at x cubed, and g of x is 2x minus 1. Find g of f of x. And now what you'll see is instead of having a value that we're going to evaluate, is just an x. So we're looking for a function, where f of x, our function f of x, is going to get plugged into our g of x function. All right, so g of f of x is going to equal 2 times our f of x minus 1. And our f of x here is x cubed. So we're just going to simplify that a little bit. G of f of x equals 2x cubed minus 1. Now it says to solve the equation of g of f of x when it's set equal to 0. So we're going to set 0 equal to 2x cubed minus 1. Add 1 to both sides. 1 equals 2x cubed. Divide by 2. And we get 1/2 is equal to x cubed. The inverse of a cube is a cube root. And then we get the cube root of 1/2 is equal to x. Now this is technically the correct answer, right? It will give you the correct value. But it is considered bad form to have a square root in your denominator, or a cube root in this case. So I'm going to go through a process of rationalizing the denominator. It means getting rid of that root in the denominator. So what we're going to do first is split up our fraction. So keeping in mind our exponent rules from before, we can break that up into the cube root of 1 over the cube root of 2. That's still going to equal x. Right? Now 1 times 1 times 1 equals 1. So the cube root of 1 is just 1. And then the cube root of 2 stays at the bottom. And I'm going to multiply by the cube root of 2 on both the top and the bottom. And now this here that we're multiplying, because it's the same on the top and the bottom, is equal to 1, right? Anything on the top, if it's the same on top and the bottom, equals 1. So when we multiply that through, you get the cube root of 2. Let me rewrite that so it's more clear. Cube root of 2 times 1 stays the same, over 2 is equal to x. Okay, then this will be our final answer. Try student example number 2 on your own.